All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Pretty good.
Good, good. Hanging in there. All right, so this week, obviously we have our midterm on Thursday, but before we do that, we do have some things to discuss, right? So I think today would be kind of a good chance to kind of just lay out the plan for the rest of the semester. So we're still finishing up our current lecture notes on 2D heat conductions. I'm hoping to finish it up today, actually. And then Thursday we have the midterm. Next week we have I have at least two lectures planned. Well, only two lectures planned. And so next week's lectures are going to be on isoparametric elements, which is what you need to do the final project. And then after that, we'll be on our final week of lecture. So I'm hoping, and we're kind of when we're on track for this, but I'm hoping that the final week of this semester, I'm not going to lecture on anything during the last week. I'm just gonna use the last two lecture periods just to be as open office hours for you guys to work on the project. Okay. So I'll be available all during the last week to answer any questions that you may have on the project, help you debug your code. Because after that, then it's kind of go time from there. Okay. Um, yeah, so that's the plan. So basically, three more lectures, including today, 1 day for the midterm exam, and then 2 days for office hours for the final project. Okay. I'm not sure what my office hours are going to be during finals week. There's kind of some other things I have to take care of that week, and so I am going to try to hold office hours during finals week, but it may not be at the same times that they're at right now. Okay, but I'll definitely let you guys know once we get closer. Okay. All right. So I think that's it for my announcements. And so I think the only assignment that's out there right now is just the final project. Any questions on anything before we get started for today? Okay. Okay. All right. So let's resume our discussion from last Thursday. So last Thursday, we were talking about basically finite element solutions to the 2D heat conduction problem um, with triangular elements. All right, so let's just do a quick refresher just to kind of make sure that kind of we're all on the same page here. Okay. Okay. So the last topic that we're covering in this class and the last topic that we'll obviously be using for the final project is 2D heat conduction. Okay. So this is our first foray into multi-dimensional finite elements. And so, we spent quite a bit of time talking about 1D problems. 1D problems is going to be the subject for your midterm exam on Thursday, right? But for 2D problems, we are essentially solving the following equation. Okay. So we have the Laplacian of the temperature plus some thermal generation term is equal to 0. Okay. Okay. And of course, if you expand this, right, the Laplacian is a specialized, vector calculus operation, but this is equal to partial squared t partial x squared plus partial squared t partial y squared plus s of x and y is equal to 0. Okay. So essentially, we're looking to solve this equation here in 2D using finite elements. Okay. All right, so of course this is the strong form. So the strong form of the equation is just the differential equation by itself, right? So we worked on developing the weak form. Okay. So the weak form, just like in the 1D case, our weak form we obtained by taking this equation here, integrating it over our domain, and then applying integration by parts in order to get all the terms that we need. Okay. So I'm not going to go through that derivation again. You can look through that derivation from last week. But basically we end up with the following. Okay, so we get double integral of the gradient of the weighting function, which is a vector, multiplied by k times the gradient of the temperature field, which is a vector, dA, okay, is equal to minus line integral around the boundary of our domain times W um, times Q, which remember this right here is our Neumann boundary condition term. Okay, plus double integral of W multiplied by S dA. Okay, so this right here is our thermal generation term. Okay, and this right here, this is our term here with the balanced derivative. Okay, so just like in our 1D problems, our weak form is going to form the basis for our finite element forms. Okay. So essentially, what we aim to do is, for our finite element forms, we're going to plug in for expressions for all of these circle terms here. Okay. And the idea is that, by applying finite elements to this, we can come up with expressions for the gradient of W, the gradient of T, or the weighting function that all involve the shape functions for our elements. Okay. All right. And so depending on the shape of the element that we have, depending on the shape functions, we should be able to obtain those things. Okay. And so this is about where we stopped last Thursday. But what we said was that here's our weak form. We're going to try to derive the element stiffness matrix for a triangular element. Okay. Okay. So a triangular element. Let me go ahead and draw it right here. Okay. Right. So a triangle has three sides. It also has three nodes. Right. Each of the nodes we know its XY coordinates. So x1, y1, x2, y2, x3, y3. All right. We can use those nodal coordinates to obtain the shape functions. Okay. And since we have three nodes here, we're gonna have three shape functions. Since we have and one, and two, and three. Okay. Right. So I'm not gonna write their expressions again just because they're a little bit long, but just know that these should be in your notes from last time. Right. But kind of the important point to remember there is that the number of shape functions that you have depends on the number of nodes that there are in your element. Okay, so for a triangle which has three nodes, we have three shape functions. Okay. Okay. All right. And so in addition to the shape functions, we also have their corresponding derivatives, right? And since we're in multiple dimensions here, we're going to have derivatives both in the x direction and the y direction. Okay. So we're going to have partial n1, partial x, partial n2, partial x, partial n3, partial x, and all the y derivatives as well. So partial n1, partial y, partial n2, partial y, partial n3, partial y. Okay. So since our shape functions are known, our shape function derivatives are known as well. Okay. Right. And then based on the fact that we can use our shape functions to come up with an approximation for t and w. Okay. Okay. So you have t is equal to t1 and 1 plus t2 and 2 plus t3 and 3. Okay. Same thing for w. W is w1 and 1 plus w2 and 2 plus w3 and 3. Okay. So we're basically just taking a linear combination of all the shape functions for a given given unknown together with the nodal values. Okay. And then these functions here, or these representations, we would plug these directly into our weak form. Okay. All right, and that's pretty much exactly where we left off from last time. Okay, but that's just a very quick summary of kind of the entire process that we followed up until this point. Okay, now of course for the project, you know you're not necessarily going to be deriving these from scratch, although you may want to add details like this into your methodology section, but I think it is really important to kind of see kind of the progression in terms of how we got to where we did, right? So remember, for traditional finite elements, or I would say, I guess this is more modern finite elements, we always start with some differential equation, right? We take its weak form, so we convert it to the weak form using our integration techniques. Then we take our weak form and we apply that directly to our element, and our element is going to have certain shape functions that we can use. Okay, so that's kind of the idea of this entire section here. The entire kind of whole second midterm is this is kind of the process that we follow, both for 1D and 2D finite elements. Okay. Okay. All right. Any questions on just kind of the summary of the whole process or just anything that we've covered so far? Yes.
Can you repeat that process again?
Yeah, so the process is, we always start from the strong form of an equation. So, for any finite element problem, there's going to be some underlying differential equation that we're trying to solve. That goes for 1D and 2D. Second step is that we take that strong form, we convert it to the weak form. So we basically get it into an integral form with balanced derivatives. Then from the weak form, we can then apply the finite element form on top of that. And to do that, you need the shape functions for the elements that you're looking at. Okay. Yeah. So it goes strong form, weak form, finite element form. Finite element form involves the shape functions. Any other questions before we continue? Okay. All right. So let's get back to kind of where we were. Okay. So if we look at our weak form here, right? Remember, the reason I put this in this form is that this kind of is the structure of our finite element problem that we're going to do eventually, right? So the first one or the first integral that we're going to evaluate here is the integral with the balanced derivatives. That's because this one here becomes our element stiffness matrix. Okay. And I'll show you exactly how we get a matrix from this guy right here. Okay. Okay. Because if you look at this integral that I've just circled in green, you can see that they involve the gradients of W and the gradient of T. Okay. Now, W and T, these are functions of multiple variables now, right? So these are both functions of X and Y, right? And so if we look at the gradient of, let's look at the gradient of T first. Okay. Gradient of T is going to be, right? We have a vector. So that's T1, partial N1, partial X, T2, partial N, or excuse me, partial N1, T1, partial N1, partial X, plus T2, partial N2, partial X, plus T3, partial N3, partial X, right? So that's all the X derivatives, and then we have the Y derivatives now as well. So T1, partial N1, partial Y, plus T2, partial N2, partial Y, plus T3, partial N3, partial Y. Okay? And we can get a similar expression for the gradient of W as well. Okay? Okay. And so if we take this, right, we can basically take this gradient here and we can put it in matrix form, right? Because one thing that we notice is that every single or both components of this have T1, T2, T3. Okay. And so what we can say is that the gradient of t, we can turn this into basically a 2 by 3 vector, right? So this vector here is going to have all of the shape function derivatives. So it's going to be partial n1, partial x, partial n2, partial x, partial n3, partial x, and then all the y derivatives as well. Okay. Multiplied by our nodal temperature vectors, T1, T2, T3. Okay. Okay, so if you do the matrix vector multiplication of these two, so our first matrix here, this is a 2 by 3. Our second vector here is a 3 by 1, right? And so our inner dimensions here agree, so then we can perform this matrix vector multiplication. We should get this thing up here exactly. Okay. So these two representations for the gradient of t are identical. It's just one we put in matrix form just to make things a little bit more convenient for us. Okay. Okay. So we can take a very similar expression and compute gradient of w same way. Okay. Okay. So I believe we did get that to that last Thursday, so that expression should be in your notes. Okay. And so if we take both of these gradient expressions and we plug it into our weak form, okay, right, because we're essentially plugging for the gradient of w and the gradient of t, we should get something that we can actually multiply. Okay. And the result is a 3 by 3 element stiffness matrix. Okay. Which is a little bit easier said than done. You'll see that the expression is not that nice. Okay. Okay. So if we plug it in, our double integral becomes the following. Okay. Okay. So first we have the coefficients of the weighting function. So W1, W2, W3. Right? Since those are constants, we can pull them out of the integral. Okay, so we still have a double integral. Our double integral is still involves K, right? So the thermal conductivity is still part of our integral here. Okay. Right? But now we have the result, right? So now we have the result of basically our two gradient matrices multiplied by each other. Okay, so this is going to be a 3 by 3 matrix. You might be wondering why I'm making such a big space for a 3 by 3 matrix. You'll see, right? This is not a nice one to write because this 3 by 3 matrix here involves basically just the matrix multiplication of all of these shape function derivatives. Okay. So you can think of this as, every kind of possible combination of shape function derivatives kind of multiplied by each other and added. Okay. All right. So I'll write maybe the first. We'll write the whole thing just for completeness. Okay. Just because, if you want to do your final project using this method, then you can do this method as well. Okay. So even though the final project specs, tells you to use the isoparametric method, if you want to just brute force it and just go based on the triangles, you can do it this way as well. Okay. Okay, so our element stiffness matrix looks like the following. So we have partial n1, partial x, partial n1, partial x, okay, plus partial n1, partial y, partial n1, partial y, okay? So that's just the first entry in this matrix, right? The top left entry, right? You'll start to see a pattern, after once we kind of start doing this, but that doesn't make it any less painful to kind of write the whole thing, okay? Okay, second column. So second column, first row is going to be partial n1, partial x, partial n2, partial x, plus partial n1, partial y, partial n2 partial y. And then third column is partial n1 partial x, partial n3 partial x, plus partial n1 partial y, partial n3 partial y. All right, so hopefully you're starting to see the pattern. So basically, we're taking a dot product between our two kind of shape function derivatives, where we have two x derivatives multiplied by each other plus two y derivatives multiplied by each other, and then the actual shape function that we use correspond to the row and column of the element stiffness matrix. Okay, so we just did the first row, right? So our second row, we're gonna have partial n2 partial x, partial n1, partial x, plus partial n2, partial y, partial n1, partial y. Okay. So you can see for that second term there, we have we're in the second row, so we start with partial n2, but we're still in the first column, so we have partial n1. Okay. Okay. All right, next we have the middle the middle entry there. So it's partial n2 times partial n2. Okay. And then we have partial n2, partial x, partial n3, partial x, plus partial n2, partial y, partial n3, partial y. Okay. Okay. All right, and then the last row. So last row, I'm just going to go fairly quickly because hopefully you guys start to see. But for the last row, we're in the third row, so that means the first shape function derivative in each expression is going to be n3. Back to partial n3, partial x, partial n1, partial x, plus partial n3, partial y, partial n1, partial y. Okay. Partial n3, partial x, partial n2, partial x, plus partial n3, partial y, partial n2, partial y. Okay. And then we have 3, 3 here. So partial n3, partial x, partial n3, partial x, plus partial n3, partial y, partial n3, partial y. Okay. All right. So technically, yes, technically we have a 3 by 3 matrix here. It's just a not a very convenient 3 by 3 matrix. Okay. Just remember that, for the most part, we're not doing any of these 2D problems by hand, right? There's a reason I kind of cut off midterm 2 at the 1D stuff. Even though this looks very intimidating, you're going to be writing code to compute this question. Yes.
Does the order of the partial n1 and partial n2 matter?
No. Yeah. So remember, multiplication is commutative. So I only did it this way just to kind of make it clear, which row and column it is. But you can definitely switch it up. And so like for this one here, right? You can definitely do partial n1 partial x times partial n2 partial x. It's the same thing.
So can we assume it's symmetric? So
It is symmetric.
Copy
Yes.
half
Yep.
when you have it.
Exactly. Right. So this element stiffness matrix follows the same rule as all the other element stiffness matrices we've discussed in the class. So this matrix is symmetric. And so technically, you only have to compute just the upper portion or the bottom portion. You technically only have to compute these entries here, then you can just reflect the matrix and get the other ones as well. Okay. That's definitely very useful if you're doing a rectangular element where you have a 4 by 4 matrix. Yeah. Great observation. All right, any other questions on this element stiffness matrix here? Okay. All right, but one thing you can't forget is that, remember, this is an integral, so we still have to integrate with respect to A, okay? But generally for a 2D triangle, all of your shape function derivatives here will be constant, right? And so if all your shape function derivatives are constant, you could just pull the whole thing out, and you only just have integral of area, which is just area. Okay. And then technically speaking, we have our nodal values here as well. So T1, T2, T3. Okay, but of course, the most interesting part here, of course, is the shape function, is the element stiffness matrix there. Okay. Okay. So we can come up with similar expressions for the element forcing vector. Okay, so if we go back up to our weak form, okay, right. So if you look at the right-hand side of this equation here, we have the term with the Neumann boundary condition and the term with the thermal generation. Okay. And so, we can come up with similar expressions here, except these ones are a little bit simpler just because we don't have derivatives to take care of, right? This is just the weighting function just straight up. Okay, so for the right-hand side of the weak form, we come up with similar expressions, right? Which will comprise our element forcing vector. Okay, so let's go through them one by one, and then you can just see that we're just going to plug in for that. Okay. Okay. So first we have the line integral, or I guess the negative of the line integral of our weighting function multiplied by our heat flux ds. Okay, so remember this was our Neumann boundary condition term. Okay. As we plug in for W here, we get minus W1, W2, W3, right? And again, we're putting it in vector form multiplied by a line integral of N1, N2, N3, okay, times Q dA. Okay. And then we have our source term as well. Okay, so our source term is double integral, or I should say, I apologize. I keep interchanging a source term and thermal generation term. So this will be our thermal generation term. Okay. All right, so similar to our Neumann boundary condition term, we're plugging in just straight for W there, right? So we plug in for W, we get W1, W2, W3, multiplied by double integral of N1, N2, N3, S of X and Y dA. Okay. All right, and so if you look at both of these expressions here, they're both 3 by 1 vectors, right? Of course, ignoring the weighting functions and the weighting values in front here, okay? But the integrals themselves, these are both 3 by 1 vectors, okay? And so if we add them together, those will make up our element forcing vector. It's just that usually for these ones, the integration is a little bit more complicated. So just because, we don't have the shape function derivatives anymore, now we have the shape function straight up in our integral expressions here, okay? And our shape functions, remember, they are linear functions in X and Y, okay? So when you compute your element forcing vectors, it's very similar to our 1D case. these usually involve some kind of integration that's non-trivial. Okay. All right, but to do that integration, just like we did in the 1D case, we try our best not to actually evaluate any integrals, at least not analytically, and so we're going to use Gauss quadrature to evaluate these integrals. Okay, but that would probably be the last thing that we talk about. Okay. All right, so that's our element forcing vector. So you would compute these two, you add them together, and they comprise your forcing vector. Okay. One thing to keep in mind though is that since we're in 2D, we're gonna have multiple elements bordering the Neumann boundary condition. It's no longer just gonna be one element, and so that's one thing you have to kind of keep in mind. Whereas for our 1D case, when we computed this Neumann boundary condition, right? Before we only computed it for a single element, just because that was the only one bordering the Neumann boundary condition. But for 2D and 3D, you can have any number of elements bordering the Neumann. Okay, so then all of a sudden, this term here that I've circled in yellow becomes a lot less trivial because you're very, very likely to have multiple elements where this applies to. Okay. And actually doing that and kind of finding out which elements actually border the Neumann boundary condition is actually not trivial. And that's why it's part 3 of your final part. Okay. Okay, any questions on this before we do an example real quick? Okay, all right, so let's do an example. We're just going to do the computations for one element, just so that you can see, and then hopefully this example convinces you that, it's not practical to do these problems by hand. Okay. Okay, so let's look at the following element. So we have a triangular element here, right? We have the coordinates of all the nodes, and so we know this node here is at 0, 0. This node here is at 2, 1, and then this node up here is at 1, 2. Okay. And then just for the sake of us doing computations, we'll just arbitrarily label the nodes, and so we'll say the bottom left node is node 1, the node on top is node 2, and the node on the right is node 3. Okay. Okay. So we have the nodal coordinates for every single element here. And so what we want to do is if we assume that our thermal conductivity is 6, okay, what we want to do is we want to compute the element stiffness matrix for this element. Okay. Okay. And so in other words, we're going to be computing this monstrosity right here. Okay. Now it looks like a lot, but remember there's only about 6 unique terms here. So we need we need all of our shape functions first of all, so n1, n2, n3, and then we need their derivatives as well. Okay, so you can account for the x and y derivatives of n1, n2, n3. That's only 6 expressions that we need. It's just repeated over and over and over again in this matrix here. Okay. All right. Any questions on just the setup for this problem? Okay. All right. So let's compute our shape function derivatives. right? So I didn't write them out today, but they were in your notes from last time. But let's write out all the expressions again. Okay. Okay, so let's first compute partial n1 partial x. And so if you look back in the notes, this is y2 minus y3 divided by 2a. Okay. Or y2, y3, those are the coordinates for the nodes 2 and 3. And a here is the surface area of this triangle. Okay. Okay. So y2, y3, we can just read those off directly from the figure here, right? So y2 is the y coordinate for node 2. So in that case, that's number 2 there. And then y3 is going to be the y coordinate for the third node, which is just 1. Okay. All right. So in the numerator here, we have 2 minus 1. Very straightforward. Okay. But what about the surface area? Okay. Right. So if you ask, even maybe like an eighth grader, right? So if you ask an eighth grader, what's the area of a triangle, right? You would say the area is 1/2 base times height, right? But that formula only works if you have a right triangle. And here we do not have a right triangle. Okay. So we need an expression for the area of a triangle for an arbitrary triangle like this. Okay. Which is probably a formula you've never seen before. I've honestly never seen this formula before either. But it turns out that if you know the XY coordinates for every single node in your triangle, there is a formula that you can actually use to compute the area. Okay. And so it's 1/2 times quantity x1 times y2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2. Okay. All right, so all you need to compute the area is just the x and y coordinates for every single node in your triangle, which coincidentally we have, right? So x1 is 0, y1 is 0, y2 is 1, y2 is 2, x2 is 1, then x3 is 2, y3 is 1. Okay. So actually, if you plug it in, right? So I'll let you guys do that. You guys can plug in numbers into an equation. Our area is actually 1.5. Okay. All right. So I know I embedded this formula into an example here, but if you did want to use this technique for the final project, you're going to need this formula here. Okay. So this formula, I'll just kind of put a box around it. This here is area of a triangle. Okay. Based on its nodal coordinates. Okay. Okay, so you plug those in, and then what we get from this whole thing is that partial n1 partial x is 1/3. Okay, next let's compute partial n2 partial x. So partial n2 partial x. Okay, the expression for this is y3 minus y1 divided by 2a. Okay. Okay, so we compute this, and so y3 in this case is 1, y1 is 0, and so we divide by 2. This is also 1/3. See? Okay, next we have partial n3 partial x. Okay, so the expression for partial n3 partial x is y1 minus y2 divided by 2a. Okay. All right, so y1 is 0, y2 is 2, so 0 minus 2 is minus 2, divided by 2a is 3, so this is a minus 2/3 here. Okay. All right, then we have the y derivatives. So y derivatives, we have x3 minus x2 divided by 2a. Okay. So x3 is 2, x2 is 1, and so we have 2 minus 1 divided by 2a, which is a positive 1/3. Okay. Okay. Next, we have partial n2 partial y. This is x1 minus x3 divided by 2a. Okay. So x1 is 0, x3 is 2. So 0 minus 2 is a minus 2/3. Okay. And then we have partial n3 partial y. Partial n3 partial y is x2 minus x1 divided by 2a. Okay. x2 is 1, x1 is 0, and so we have 1 minus 0 is 1 divided by 3, which is 1/3. Okay. Okay. So that's the easy part. So the easy part is computing the shape function derivatives. Now the fun part, just which in the interest of time we are going to skip. But just know that now that you have your 6 shape function derivatives, you can then take these expressions and plug it into this monstrosity right here. So you're going to have a lot of plugging in, a lot of multiplying, a lot of adding. But it is, it will be tedious. I'm not saying that it's not going to be, but it is fairly straightforward. Okay. But again, you're not, remember, for the most part, you're not computing these by hand just because it's just not practical. But you would have a computer basically do this for you. Okay. So the way this would work in code is that, let's say that you're using this method, you want to use it for the final project, within your loop, right? So you're going to loop over every single one of the elements. Within your loop, you're going to compute your 6 shape function derivatives. Okay. So just like, for our 1D problems, just like for our direct stiffness problems, you're going to have a loop that's going to loop over every element. And you're going to compute the element stiffness matrices for each loop. Okay. So for 2D problems, it's no different. So you're going to have a loop that loops over all the elements. And within that loop, right, you're going to compute the 6 shape function derivatives. Okay. Then once you have your 6 shape function derivatives, you would then just code the formulas for each entries of the element stiffness matrix to compute their values. Okay. So, it's very similar to our frame code, right? So if you think back to our frame code, right, all of the expressions or all of the formulas in our element stiffness matrix for the frame, not practical to compute by hand. But, all you would have to do is just input those formulas into your code, and then it can compute that for you. Okay. Okay, so if you're curious what it is for this particular problem right here, if you wanted to check your work later, okay, okay. And so if you perform the arithmetic, you basically plug in for everything, you compute everything, you get the following 3 by 3 matrix. Okay, you get 2 over 9, 0, minus 1 over 9, 0, 8 over 9, minus 6 over 9, minus 1 over 9, minus 6 over 9, 5 over 9. Okay. right? So that's the matrix that you get by applying all of our shape function derivatives. Okay. So is this our element stiffness matrix? Not quite, right? So remember our element stiffness matrix, this is definitely the biggest, the most time-consuming part. But remember that our element stiffness matrix also involves a double integral and it involves our thermal conductivity as well. Okay. Okay. So our element stiffness matrix involves a double integral of K multiplied by our matrix. Okay. Integrated over the area of the element. Okay. Right. So that 3 by 3 matrix, that's just what we just computed here, right? So that goes there, but then we also have to multiply by K multiplied by integral of area. Okay. And now since our element stiffness matrix here is all constant, our thermal conductivity is also constant. Okay. That means we're just going to be multiplying this by a constant factor, right? So we're going to take double integral of K dA. Okay. Okay. Which, if we integrate this, this is just K multiplied by the surface area of the element, right? Because K does not change with space, right? We know what K is, and so for this problem, we were given that K is equal to 6, and we know the surface area, which is what we computed using our area formula from before, right? So we have 6 times 1.5, which is 9, right? And so we multiply that by this. Okay. And that gives us our element stiffness matrix, right? And then so conveniently, just because I picked the numbers to be so, the 9 that we obtained from the K times the area is going to cancel out with the 9 in the denominator for each of the terms. Okay. Okay. So I know for that example, we didn't really do much computing other than the shape function derivatives, but remember, from this point in the class, we're shifting our focus more towards the final project. And so, we're not doing any more computations by hand, but you should know kind of the steps of the algorithm, the steps of what you need to compute. And so then you can implement those and instruct the computer to do those through your code. Okay. All right. Any questions on this example here? Okay. All right, so that's everything about the 3-node triangle, right? And so, again, if you want to use this method to compute the element stiffness matrices in your final project, you can definitely do that, right? And so, we're using linear shape functions for the final project, so this will apply. Okay. But the 3-node triangle is not the only element that we have available to us in 2D. Okay. So the other main element that is out there is the 4-node rectangle. Okay, so let's discuss the 4-node rectangle. And in fact, the 4-node rectangle is going to be the basis for our discussion on isoparametric elements, which we're going to do after the midterm. Okay, so just like the name implies, the 4-node rectangle has 4 nodes, okay, which makes sense because it's a rectangle, right? And so there's 4 sides to a rectangle. There's also 4 vertices in a rectangle, okay? And so just like before, we can label all of the nodes. Okay? Doesn't really matter which order that you label them in, but I just like to go counterclockwise, right? And then for each of these nodes, we also know their XY coordinates. Right? So we have X1, Y1, X2, Y2, X3, Y3, and then X4, Y4. Okay. Okay. All right, and so if you compare this element here to our three-node triangle, there is one additional node that we have. Right? Kind of stating the obvious, but it's worth making note. Okay. Now mathematically, this does have a consequence, right? And so that means that our shape functions, first of all, we're going to have one additional shape function, right? Because remember, the number of shape functions that we have matches the number of nodes that we have in our element, right? So if we have four nodes, it means we have four shape functions. Okay. But this also has another very actually important consequence as well, because the number of nodes in your element not only determine the number of shape functions, but it also determines the number of degrees of freedom that we have in our shape function as well. Okay. Let's see. Okay. Okay, so what does that mean? So what does it mean to have one more degree of freedom? So let's write out the general form um, of our solution function. Okay. Right. Remember, for any finite element problem, we have to assume a form of the solution. Okay. And this is where we apply our assumed form. So, we still want to have a linear function. So that has not changed. Right? And so our assumed form of the solution is going to be a function of x and y. So we have t, function of x and y. Let's write out our first three terms that come from the triangle, because those are going to be present here as well. Okay. So if a0 plus a1 times x plus a2 times y. Okay. So we have our constant term a0. We have our terms that are linear in x and y, a1 and a2. Okay. But we need one more, right? So remember this. So this assumed form only has three unknown coefficients, a0, a1, a2, but we have four nodes, right? And we have to make use of that fourth node. We can't just leave it out of the party, right? But we've run out of linear terms, right? So we can't really have another linear term, like we can't have another a3x, because a3x would be the same thing as a1x, right? So the fourth term that we add here has to be unique, right? It has to be a new degree of freedom, but we don't have any more linear terms available to us, right? So we can't have x, we can't have y, we can't have a constant. And so our only option is to create what's called a pseudo linear term. Okay. Okay. So the fourth term of our assumption is going to be a3x times y. Okay. So it's actually going to be the product of x and y. So by itself, right? So by itself, x times y, technically that's a nonlinear term because you have the multiplication of two independent variables. Okay. But if you look individually in x and individually in y, this term is linear because it's only x to the first power, y to the first power. Okay. So this fourth term right here, we call the pseudo-linear term. Okay. Because even though it's technically a quadratic term, we treat it like it's a linear term because it's linear in x and y. Okay. Okay. Good. So now that we have a form of this assumed solution, we can now solve for the coefficients in this expansion here, and that's going to give us our shape functions. Right, remember the way that we do that is that we enforce the nodal solutions at each of the nodes of our element. So we solve for A0, A1, A2, and A3 by enforcing the nodal solution. So remember, for each node in our element here, we have a corresponding nodal solution T1, T2, T3, T4. Right? Because that was our continuity requirement. So our continuity requirement says that, our nodal solutions have to match when you go between the elements. And so the way that we do that is we enforce that nodal solution. Okay? And so if we do that, we can rewrite our assumed solution form. We can rewrite T of X and Y is equal to T1 and 1 plus T2 and 2 plus T3 and 3 plus T4 and 4. Okay? All right. And so if you go through the math, if you go through the kind of the hassle of computing N1, N2, N3, N4, you get the following expressions here. Okay? So you have N1 of X and Y is equal to X minus X2 divided by X1 minus X2 times Y minus Y2 divided by Y1 minus Y2. Okay. Then we have N2 of X and Y is equal to X minus X1 divided by X2 minus X1 multiplied by Y minus Y2, or excuse me, Y minus Y1 divided by Y2 minus Y1. Okay. Sorry, there was one assumption for these equations. I'll make note of it right after this. Okay. You'll notice that there's no x3, x4, y3, y4. There's a reason for that. Okay. All right, and then n3 of x and y is equal to, let's see, we have x minus x1 divided by x2 minus x1 multiplied by y minus y1 divided by y2 minus y1. Okay. And then n4 of x and y is equal to x minus x2 divided by x1 minus x2 multiplied by y minus y1 divided by y2 minus y1. Okay. Okay. So the reason you don't see x3, x4, y3, y4 here is that I did make one assumption that I forgot to mention. Okay. So these formulas assume, okay, we're basically making the assumption that our rectangle here has perfect right angles on its interior. Okay. So that means that node 4 is right on top of node 1. Okay. And then node 3 is right on top of node 2. Okay. Okay. And so in other words, we have the following situation. Right? So we have our rectangle here, right? We still have node 1, 2, 3, and 4. Okay. Right. So node 1 here is still going to be x1, y1. Okay. And we're also making the assumption that node 1 and node 2 are on the same horizontal line from each other as well. Okay. So that means the coordinates for node 2 here are actually going to be x2, y1. Okay. So it's going to have the same y coordinate as node 1, right? So we just move to the right by x2. Node 3 here is going to be x2, y2. And then node 4 here is x1, y2. Okay. I apologize for the confusion. So I did miss that in my notes, okay? But just make sure you kind of note that here. If we didn't have that assumption, if we didn't assume that we have kind of a perfect right rectangle, then the equations kind of get out of hand. Okay? Question, yes.
For N4, isn't it supposed to be y minus y2 over y1 minus y2 then?
That one is correct. I think, let me see. I'm sorry, I'm N2 is actually messed up. So N2 should be y minus y2. This should be y minus y2, y1 minus y2. Yeah, so I apologize. So for the expression for N2, I did make a typo on these terms here. Okay, so make sure you do correct that. Yeah, that should be right. Okay. Okay. All right. Any questions on this so far? Okay, good. All right, so these shape functions, when they're in this form, I would say they don't look as intimidating. But if you kind of FOIL this out, right? So if you look at every single one of these shape functions, they all involve the product of two kind of of two terms here. Okay. Right. So let's say that when you take the product of those two terms there, right, and you can just look at the first term in that product, you're going to get a term xy, right? Which makes sense, right? Because that's exactly kind of what we started with. And so what we started with is an assumption that our t of x and y, that we are going to have a term here that has x times y. Okay. Okay. But that's actually very significant. And it's significant in the sense that it makes our life actually pretty miserable when computing our element stiffness matrices. Okay. Because when we take the derivatives of these shape functions, okay, and first of all, there's more derivatives to take because there are four shape functions, right? And so you're going to take x and y derivatives of each of those shape functions. And so that's 8 derivatives that you need. Okay. But that's not the worst part, right? The worst part is the fact that because we have an xy term there, when we do take the derivatives of our shape functions, we no longer get a constant, right? All of our shape functions here are actually going to depend either on x and or y. Okay. So one of the benefits of the triangle is that, because we had a pure linear function, when we took its derivative, we ended up with a constant. And that made our computation of the element stiffness matrix not necessarily easy, but at least convenient because when we integrated it, all the constants kind of just came out of the integral. Okay. So for instance, if you take partial n1 partial x, okay, you get y minus y2 divided by the area. Okay. Which is not a constant because now we have y that's in our shape function derivative here. Okay. Okay. And so eventually, when we do plug this into our weak form, okay. And so remember, our weak form is the following. So we have double integral of gradient of w multiplied by k multiplied gradient of t dA. Okay. Right. So our shape function derivative it's going to be part of our gradients here, right? So we're going to plug it in here, plug it in here. Okay. Eventually, we're going to get a term, right? So let's say this is in our element stiffness matrix. partial n1 partial x, partial n1 partial x, plus partial n1 partial y, partial n1 partial y, right? We're going to get a lot more terms like that. Right? Okay. But since our shape function derivatives are not constant anymore, that means we can't just pull it out of the integral, right? So we'd actually have to integrate this. Okay. And that is a huge pain in the butt, right? To kind of put it lightly, right? That's something we absolutely do not want to do, especially not in an analytical fashion, okay? So what is our solution to this, right? So what is our solution to doing these integrals? Well, it's the same solution as our 1D problems. Let's, instead of evaluating the integrals analytically, we can instead evaluate them numerically using Gauss quadrature. Okay. But now, instead of Gauss quadrature in 1D, we have Gauss quadrature in 2D. Okay, and that'll be the last topic that we discuss today. All right, any questions on any of this before we go over Gauss quadrature? Okay, all right, so let's go over Gauss quadrature in 2D, or at least introduce the idea. All right, and so if you recall from 1D, right, Gauss quadrature was a way that we can use to, evaluate these integrals, right? And so we have integral. Okay. And very important, in order for Gauss quadrature to work, we have to have integration bounds from -1 to 1, okay? And so in 2D, that means both of the integration bounds of our double integral have to be from -1 to 1, okay? Of f of x and y dA, okay? What we can say is that instead of taking the antiderivative and performing this integral, we can instead evaluate this as a weighted sum, okay, of the integrand. Okay. And so we would have summation I of some Gauss weight I, okay, not to be confused with our weighting function. So this W here, this is our Gauss weight. Okay. Multiplied by F of Xi, Yi. Okay. So the idea is to evaluate our integrand at certain key locations, okay, called the Gauss points. Okay. We multiply each integrand evaluation by a weight. We add them up together, and that will give us the result of our integral. Okay. Okay, and so by doing Gauss quadrature, we avoid the problem, or we avoid the issue of taking an antiderivative, which is probably the most time consuming and part that the computer honestly can't do. Okay. And so as long as we have an expression for the integrand, and as long as we can do this weighted sum, then we can compute any integral that we want numerically. Okay. Okay. So the idea of Gauss quadrature doesn't change. The main thing of Gauss quadrature that changes in 2D is the location of the Gauss points and the weights. Okay, so this is the same idea as 1D, only thing that changes. Okay. All right, so in 1D, we discussed, three different possible Gauss rules. We covered the 1-point rule, the 2-point rule, and the 3-point rule. Okay. In 2D, it gets a little bit, it changes a little bit. So there is a 1-point rule in 2D, but then after the 1-point rule, the next one is actually a 4-point rule. Okay, so let's go over both of those. So this is the 1-point Gauss rule in 2D. Okay. So this is probably the simplest one we can do. Right. And so remember, our integration bounds here go from -1 to 1 in both the x and y direction. Okay. That means our integration bounds look like the following, right? And so we're basically integrating over a square. Here is our origin here, right in the middle. Okay. Right. And so if our origin here is 0, 0, right? This right edge here is 1, 0. Left edge here is -1, 0. Top edge right here, this is 0, 1, and then 0, -1. Okay. So it's basically a square with the length of each side is equal to 2, centered on the origin. So the 1-point rule is very easy. So 1-point rule basically says that we're going to evaluate our integrand right in the middle, right? So we're just going to evaluate the integrand at 0, 0, and then multiply it by 4 to account for the area of our triangle, of our rectangle here. Okay? So the 1-point rule, very simple. Integral from -1 to 1, integral from -1 to 1 of f of x and y dA is simply equal to 4 times f evaluated at 0, 0. Okay. All right, let's do one very, very quick example, right? Just to kind of hammer home this idea. Remember, for Gauss quadrature, you're not actually performing any integration. You're not doing any antiderivatives. Okay. And so if we want to evaluate the integral from -1 to 1, -1 to 1 of x squared plus x squared times y plus 3 dA. Okay. Okay. And so let's say that we want to evaluate this using the 1-point rule. We're going to take our integrand here, okay, x squared y plus 3, and evaluate it at x is equal to 0 and y is equal to 0. And so the integral is 4 times 0 squared times 0 plus 3, okay, which is 12. Okay. Or the expression here in parentheses, this is f of 0, 0. Okay. All right, so Gauss quadrature is great in 2D. We'll go over the 4-point rule after the midterm. I think that'll be kind of a good segue into isoparametric elements anyway. So we'll stop here for today. So Gauss quadrature is great. It avoids us having to take any integrals, but the same problem still persists in 1D, right? In order to use Gauss quadrature, we can only use it if our integration bounds are -1 to 1. Okay, but I would say for the vast majority of cases, that's not going to be the case. And so we're going to be performing integrals on arbitrary integration bounds. And so the question now becomes, how do we take 2D Gauss quadrature and how do we generalize it for a general 2D finite element? And so if you recall what we did in 1D, what we did was we just did a very simple kind of change of variable. So we're going to do that again here. It's just that in 2D, it's not so simple. So there's actually quite a few steps to it. And so this leads us into the very final topic of the class, which is called isoparametric elements. Right, and I will leave you on that thought. And so when we come back on Thursday, we're taking our midterm. But then when we come back to lectures next Thursday, we'll talk about the 4-point Gauss rule next Thursday, or next Tuesday, excuse me. And then we'll start going over isoparametric elements. Okay. All right. So thank you guys for coming today. If you have any final questions before the midterm exam, I have office hours on Thursday. If otherwise, you can always email me any question that you have. Best of luck studying. I will see you all Thursday, and I hope you have a good rest of your day. Right. What's up?
Yeah, I had a question on the
Okay.
your own job.
Yeah.
So really, the abstract we submitted to the I mean,
Yeah.
so I'm not sure because
It's
necessarily.
fixed, right? Yeah, I saw that. If it's fixed already, then that's fine.
Okay.
Just that was just kind of my personal preference. Is usually you have kind of acknowledgements at the end, but if it's already submitted and accepted like that, let's keep it the same.
Okay.
Yeah.
And then there was one comment where Josh was trying to on the first sentence of the paper, essentially, he was trying to just not specify, but he was basically reiterating the abstract a little bit.
Yeah.
But that was one of the ones where you're like, okay, maybe we could delete this. Yeah, I don't know. I'm sure it probably would make more sense.
Okay. Yeah. Let's. There's another class coming in, so I'll come to you.
Even a midterm too, there's only like one thing we had before that here.
Yeah. It's almost free. Yeah.
I don't think there was Gauss quadrature on that one, right?
There was not. So Gauss quadrature, you will have to kind of practice on your own, but it is on the practice midterm.
Yeah.
Yeah.
Anything they got any solution for that?
There is not, but that also all those integrals you should be able to evaluate normally anyway. So you should be able to factor in.
Okay.
Yeah. See you guys.
Get around.
You know,